just fine. We can get plenty done in 30 minutes. All right. So in the simulation last time, you did a simulation on wire resistance, and you had the straw. And to quote a certain individual, the longer it was, the harder it was to blow. Which hopefully will stick with you when it comes to wire resistance. And the reason I mention that is not only is there almost always a question about wire resistance, it was actually one of the questions on my physics test when I took the physics test last month. And it was about various conditions about what wire would have the most resistance. So to sum up, a wider wire, a thicker wire, has less resistance. Okay? As wire diameter increases, resistance decreases. As wire length increases, resistance increases. So in other words, a longer wire has more resistance, and a thinner wire has more resistance. And this is kind of interesting. You weren't able to test it in the simulation, but it is something that's very important. It's extremely important. As wire temperature increases, resistance increases. So wire temperature and resistance are they increase together. Now, what device in your home uses this principle?
Light bulb? Microwave.
Nope. Well, sort of, but toasters are a little weird because they're non-ohmic. But it's an ohmic device. In other words, it doesn't glow when there's a lot of voltage put across it. But as this device, in this device, there's a little wire, and the temperature tells the device how to operate. Yeah, your thermostat that controls your AC, your heater. There's a little wire and a little microcomputer that measures its resistance. And as the temperature in your house goes up, its resistance goes up, and that tells the microcomputer what the temperature is of your house. There's one in your car, actually several in your car too. The amount of oxygen that goes into your car varies with the temperature of the atmosphere. So there's a mass oxygen sensor called a mass air sensor that measures how much oxygen it gets. We use the same principle. Your air conditioner in your car uses the same principle. It's pretty important. My guess is there's some in your cell phones too. If your cell phone gets too hot, assuming it's not a Microsoft Note, if your cell phone gets too hot, your CPU is designed to power back down, slow itself down, so your battery doesn't burn itself up. How does it know how hot it is? Same principle. As wire temperature increases, resistance also increases. And then, of course, the type and the density of the material also affects resistance. While it is not a rule, the trend is the more dense something is, the lower resistance it will have. So aluminum is not very dense. It has a lot of resistance. Gold and copper are pretty dense, and they have very low resistance. The electrodes that control your airbags and your two-stage electronic seatbelts, those are all gold-plated. They have to be. Even if you're driving a Porsche or a Hyundai, they have to be gold-plated because, one, they have very low resistance, and two, they're corrosion resistant. The electrodes that control your airbag. So to make sure your airbag works 10 years after your car is purchased, all those things are gold-plated because gold has very low resistance and very high resistance to, or very high corrosion resistance. I know that's not the best word, but anyway, moving on. A potentiometer is a variable strength resistor. In older houses, we used to use potentiometers to brighten or dim lights. Yeah. So the potentiometer changes the voltage or changes the amount of current going to your lights by being a variable strength resistor. No. Newer ones for LEDs, newer homes that control LEDs, they don't use necessarily a potentiometer. But older ones where it's just a knob that you turn, that's a potentiometer. A lot of speakers use potentiometers, like amplifiers, you turn the knob. It's not an electronic amplifier. Like my boxes over here, this is a very simple amplifier. These are all connected to potentiometers that just change the resistance of each channel. That's a potentiometer. Questions before we move on? Okay, no questions? Then we move on. All right, Tesla and Edison, AC versus DC. So you might know some of the story. Hopefully with the concept crossword, you read a little bit about it. So electricity hasn't really been a big deal for more than a couple hundred years. So Edison was a champion of DC, direct current, because of its simplicity. DC is very simple. You have a positive potential or a high potential, you have a negative potential or a low potential, and charges will travel from the high potential to the low potential. And as they travel through that difference in potential, they may encounter resistance, which will slow them down and allow them to release some of their energy. That's how they work. Okay. Batteries, chemical energy, producing electrical energy, are sources of direct current. Okay? Batteries are sources of direct current. The battery in your car, the 12-volt battery in your car, the 1.5-volt batteries in your pocket that control your Bluetooth, or your rechargeable 3.7 lithium-ion batteries, those are all DC. There's a positive potential, there's a negative potential, and charges travel between the positive to the negative. Now, there's a problem with this. In small current loads or small voltage loads, DC works great. In large current loads, DC's got a problem because you have to make the wires extremely thick. And if you don't, then they heat up. So that's where AC comes in. That's how you burn down your town. AC is really great because with AC, you can curtail the amount of voltage you use, or the amount of energy you lose with high voltage, by just having it flip-flop, go positive, negative, like turning it on, off, on, off, on, off, on, off. So you can send large amounts of voltage over very long distances with very small losses in heat, which is why we use AC pretty much globally. So if you tried to plug your iPad into one of the power lines overhead, it's not going to work because it's running on AC. Like I mentioned, I think last week, in North America, the AC is running at 60 hertz. Yeah, everywhere else it's 50 hertz. I don't know why it's 60 here. So your home electricity is 110 volts at 60 hertz. If the transformers are working properly, if the transformers on each street corner or up above you, depending on how old your block is, if they're working properly, then your electricity is 110 volts at 60 hertz. Yes. Yeah.
Is there any noticeable difference between making it 60 and 50 hertz? Like, is it like fast? What change?
Yes. Most transformers that convert the wall power to what a device can use are designed to work at 50 or 60. They have an internal circuitry to make them work. But yeah, if that internal circuitry is not there, then your device will simply not work. It will not get the power as it expects to get it. So sometimes, like computer power supplies and laptops, you can usually just get an adapter and your battery will charge properly, because it takes the AC from the wall to the battery and you're no problem. Other things might not work at all. Like fans might just go slower, and some things might just not work. So what's the big block doing? Or the little block, depending on if it's an iPad or a cell phone. Yeah, it's converting the AC to the DC in a kind of an interesting way. If you were to graph the electric potential, copy this graph down. If you're going to graph the electric potential, this is going to be positive voltage. I'm going to make it positive V to negative V. The number is not important. And you were to graph it over time, what do you think the graph is going to look like? This is going to be for AC. What What do you think the graph's going to look like? Yeah, it's a sine wave. It's a sine wave. In fact, the symbol for AC is just a sine wave. If you have your charger, you can pop it out and take a look. And like, hey, look at that. There it is. It'll say 60 hertz AC 100 or 120 volts, sometimes 110 to 120 volts. And it'll have a little sign. And then it'll have an output. The output symbol for DC looks like this. It's one straight line and three little lines representing the positive and the negative potential. That's a symbol for DC. Well, how do you take, mathematically, how do you take an AC and turn it into DC? There's these things called diodes, and they only allow current to travel in one direction. So a diode, a symbol for a diode looks like this. It's a triangle inside a box. So basically it says, I'm only allowing the positives to go. So what a diode does is it just either flips the negative, depending on if it's got a capacitor stored to it, or it just cancels it out. So depending on what the quality of your AC to DC converter, it might just flip it. So what the power sees is positive, 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 or it might flip it so you get positive and positive and positive where there was previously negative. So that's what it's doing. So depending on the quality, it's taking the absolute value and only allowing the positives to go through. It's an oversimplification, but if you take electrical engineering, you can learn all about it later on. Or you can just get on YouTube and say, how does AC turn into DC? And there's all sorts of great videos on it. The most important thing is DC is for devices, AC is what comes into your house. And if we got to talk about generators, we could talk about generators, but I'm going to skip it for another time. And the reason I said you really should know about the 60 hertz is this every now and then pops up on a multiple choice question. And you just should know it's 60 hertz. OK, questions before we move on? Yeah?
Like, what do you mean it pops up on multiple choice? Like it'll ask you what the
No, it'll never ask you
problem, and you have to know it?
Exactly, yeah. It'll never ask you what is the AC current in America. What it will do is it'll give you a graph, and it'll give you a sine wave, and you'll find the frequency of that sine wave, and be like, oh, it's 60 hertz. And you should know that, oh, then it could be wall power. It could be electricity out of the wall power. Does that make sense? I wish I could give you some specifics. I just remember there was a question, but I don't remember its specifics. But it did require you to know that AC wall power is 60 hertz. Okay. Other questions before we move on? Banging right along. Okay, so elements of a circuit diagram you probably should know. I wish they were all uniform, but they're not. They're not uniform. But the most important one is that's a ground. A ground is a source of negative potential, infinite negative potential. So it can act as the negative pole of a battery or a cell. That's a resistor in North America. Someone came along later on and said, wow, that's really cool, America. I like electricity, but I'm going to make it really easier. I'm just going to make it a box and write 50 ohms in the box. That's what you see in Asia and Europe. You just see a box with a number in it.
So is that the one you like?
This is what you're going to see on the AP. You're going to see squiggly lines. Or you'll see lights. A device is usually a squiggly line with a circle around it. So you might see a light as like this, or it might be like this, or it might say 1, as in like that's light number 1. I think in all my diagrams and all the practice we're doing this week and next, it's squiggly lines labeled R1, R2, R3. And of course the battery, also pretty important. Which side's the positive potential, the left or the right? Who remembers? Yeah, the big line is the positive, the little line is the negative. And a battery is several cells. So battery means multiple cells.
of like you hit somebody, it's assault. If you hit them again, it's battery. That's how you think about it. Like a battery is multiple cells. A 1.5 volt AA battery is actually not a battery, it's a single cell. The electrochemical potential is about 1.55, 1.6 volts. It's one single chemical cell. Your cell phone at 3.7 volts is one lithium ion cell. But your laptop battery that needs 9 or 10 volts is actually multiple lithium ion cells. That's how your car battery that runs on about 12.5 volts is actually 6 2-ish cells. Yeah.
What's the difference between the electric? Oh, is there just the dot in the middle? Like electric connection,
Oh,
non-electric
that's,
connection?
it's not important.
Okay.
Basically what this means is, this is an old style of doing it, you're never going to see overlapping wires. Yeah. What it basically means is if you have a huge diagram, they can't compress everything, then it means like the wire goes over but doesn't actually connect. Yeah, that's not
Are
important.
the voltmeter, ammeter, lamp?
Yes, and that's what we're talking about next. I hope that's what we're talking about next. Voltmeters and ammeters. Okay. Any other questions about this before we move on? Capacitors are a huge part of electronics, but they're not in the AP Physics 1 test, so we're not working with them. And switches, you probably figured out how a switch works. It's open, it's closed. Okay. Okay. Give me a thumbs up if this makes sense and you're ready to move on. Okay, only about half of you.
So do we need to write down voltmeter and ammeter? But
You will in a little bit. So I think it's on the next slide. Okay, move on. Okay, so battery or cell, source of potential. It's like the electron pump. And again, I mentioned this last week, but since we've had some time to forget it, remember, when we're talking about current, we're talking about what charges? Positive or negative? Positive. Conventional current is positive charges. Do protons actually move? No. The protons are the material. They are fixed in the wire. But when we're talking about conventional current, we're actually talking about positives moving. Are the positives moving? Not really. The electrons are moving. But what's really going on is electric fields are changing. We're not going to go into huge depth about electric fields because that's physics AP2. Just you do need to know that current is the flow of positive charges. Electrons travel in the opposite direction. So current travels from a positive potential to a negative potential, or from a high potential to a low potential, and that's positive. So if our battery has a positive here and a negative here, the current flows that direction. This is the current. That's important. Really important. That current travels from the positive to negative. Resistor slows travel of charges, and just like when wind slows down as it goes through a turbine, slowing down charges allows electricity or allows energy to be extracted from those charges. Lamp motor, capacitors we're not going to talk about, and the switch, hopefully that's obvious. But anyway, so hopefully this is just what I've been talking about, and the ground is a source of low potential. So lamps and motors have resistance. They will always be ohmic. Isn't it? So lamps and resistors will always be ohmic. We're not going to deal with toasters. Okay. There won't be any toasters on the AP test. What do I mean by saying something is ohmic?
something is ohmic is something like Ohm obeys Ohm's law.
Good. So ohmic means a device obeys Ohm's law. And when we say it obeys Ohm's law, what does that mean?
It's like the same resistance until it gets like melted or something. Like until
Exactly.
it can't be or something.
Exactly. Something that is ohmic, and we drew a little graph last week. Something that is ohmic has the same resistance regardless of the potential you apply to it, regardless of the voltage you apply to it. If you have a wire and you apply 10 volts and it has the same resistance, whether you apply 10 or 100, that is an ohmic wire. If you apply 1,000 volts and the resistance is not the same, it's not ohmic anymore. So a typical graph of something that is ohmic is if you apply voltage and there's a resistance, yeah, it should be a straight line and then it should fall off. So this is where it's ohmic, and this is where it ain't ohmic.
What did you say in ohmic?
A wire that has the same resistance regardless of the potential you apply to it.
You said like something on this.
Everything.
Oh,
Everything you're going to encounter on the A/B test is ohmic.
Why is
So-
a toaster not?
Because it glows.
Okay.
Yeah, if a wire actually gets so hot it glows, it's no longer ohmic. Okay. Wow, did I not put that in there? I did, okay, we'll get into it. Okay, two types of circuits, series and parallel. A series circuit has one path, and the current has to travel through every device in the path. This is how we used to show lights. This is a diagram that's almost 20 years old. So, if in a series circuit there is one path, and the current has to travel through everything in the path. This is your nightmare when you're driving on the freeway. Construction limits you to one lane. If there is one lane, can you travel faster than the car in front of you? No. If there's only one lane, all the vehicles have to travel the same speed. If there's only one lane. Okay. So, what is the travel of charges called? Current, exactly. So, in a series circuit, listen very carefully. Just like all the traffic in one lane has to travel at the same speed, in a series circuit, everything in the series path has the same current. Because current is the flow rate of charge, how fast charges are moving. So since all the cars have to travel at the same speed, all the charges have to travel at the same speed, everything in this current loop has exactly the same current. This resistor has a current I. This light has a current I. This light has a current I. And this light has a current I. And they're all equal in a series circuit. In a series path, the current is equal for all devices. So what can we say about the current leaving the battery here and coming back to the battery here? It's still the same. It's still I. This is still I. Okay. In a series loop, the current is the same. Now, in a does that make sense? First of all, give me a thumbs up if you got that right. You're going to get this right in 5 weeks. Okay, cool. In a parallel circuit, there are multiple paths. In a parallel circuit, there are multiple paths, and each path accesses the potential source independently of every other path. In a parallel circuit, there are multiple paths, and each path accesses the battery or the cell or the potential source independently of every other path. You're going to play with circuits in a simulation tomorrow and then in real life next week. I wish I could have something set up for you, but just haven't got around to making it. What this means is this. If your battery is 12 volts, how many volts are going into this branch right here? 12 volts. And how many volts are going into this branch here? 12 volts. Make sense? Now that does not mean that 24 volts are going in, okay? Because this is potential. You can think of a series path as a waterfall that splits off in half, where one waterfall goes that way and there's a big rock in the middle, and the other waterfall goes that way. They're both falling from in parallel. You can think of a parallel circuit as having like a waterfall with a rock in the middle, and there's two separate waterfalls. They both come back to the same source of water, and they both start in the same source of water, but they have two different paths. So 12 volts leaving the battery,
You're running at the same speed?
not yet. But just, we don't know about the current yet. Because these devices might be different. But we'll get to that. So if 12 volts leaves the battery, 12 volts goes into that branch, 12 volts goes into that branch. If you cut this branch right here, this branch is unaffected. Okay, make sense? Okay. This is how your house is wired. You don't have to run your toaster to get your garbage disposal to work because they're independent. They're all wired in parallel.
Previous actually different.
You're like, I need to make a smoothie. Someone plug in the toaster oven. Start the toaster oven so I can make my smoothie. Doesn't work that way. Okay, now that's potential, guys. Current. This is important. If this current gets I, how much does this branch get? We don't know. It's going to get I2. Okay? It's going to depend, if this gets I1, this gets I2,